Hello, this lecture addresses the mechanical properties of structural steel. We'll start off with a discussion of the different rolled shapes and cross-sections that are available for engineers, and then move on to a discussion of material properties like yield strength, modulus of elasticity, etc. Much of this will be a review of what you've already learned in your materials of construction class, but we'll use this as a starting point to make sure that everyone is on the same page. Let's get started. The structural steel that we use as engineers is available in a number of different cross sections and shapes and sizes. Hot rolled structural steel is available in I-shaped sections, channels, angles, T-shaped sections, hollow structural sections or tubes, and as flat products like plates and bars. We'll discuss each of these types of shapes or cross sections over the next several slides in the first part of this presentation. Rolled I-shaped sections come in 4 different variants that are designated as a W, S, M, or HP. The W stands for wide flange shape, the S stands for standard shape, M stands for miscellaneous, and the HP stands for H-shaped pile or H-pile. So the letters are followed by 2 numbers. The first number is the nominal depth of the section in inches, and the second one is the weight of the section in units of pounds per foot. So for example, a W14 by 120 is a wide flange shape that is nominally 14 inches deep and weighs 120 pounds per foot. Now be aware though that the depth is just the nominal depth, not the actual depth. So while 14 by 120 has a nominal depth of 14 inches, the actual depth is 14.5 inches. Okay, wide flange shapes are the de facto structural members for steel buildings. So they're the buildings that are the shapes that are used most often. And they have essentially parallel inner and outer flange surfaces. So the flanges have a constant thickness over the width of the flange. There's another characteristic about W shapes that makes them quite well suited for building design. That is, the T dimension of all W shapes within a given group is the same, so that it permits section changes with different weights that when spliced together have a common inside surface for the flanges. So the T dimension of W shapes is illustrated here. This is a figure out of the AISC manual where you would look up the properties of rolled sections. And the T dimension is basically the distance from the inside of one flange to the distance to the inside of the adjacent flange. Now it does include some of the fillet between the web and the flange of the section, but basically it's the distance between the inside surfaces of the flanges. So if you take a look at one of the pages out of the W sections in the AISC manual, you can see that for different groups of W14 shapes, for example, here, they all have a T dimension of 10 inches. Down here, this group all has a T dimension of basically 1 7/8, etc., etc. That's important because when you stack these members on top of each other, like you would in a column tree, like we have shown here, the inside faces or the inside surfaces of the flanges all line up. So there's a common plane here, and there's a common plane over here, and that makes the detailing or the connection design much easier when you use members that have common T dimensions. So that's why W flanges are well suited for building members. Now, this figure actually comes out of the AISC detailing manual, and if this was a face-to-face class, I would have a copy of it and I would pass it around for you guys to take a look at. But basically, I just want you to know that there is a separate manual for detailing of steel construction, and it gives the different conventions that you would use for putting together a drawing package for fabrication or for erection of steel structures. A lot of good stuff in there. It's not nearly as expensive as the manual of steel construction. The detailing manual, I think, is probably around $50, and you could probably find a PDF copy online if you looked. So this shows another column splice. The one that we looked at in the previous slide was a welded splice. This one is a bolted splice, which creates a little bit of a different arrangement. So in this situation, you can see that there's still the common plane between the inside surfaces of the flanges of the section above and the section below. But in this case, there's a gap that needs to be accommodated. If we look at the outside surface of the flange for the section below and the outside surface of the section above, there's this gap in between there that needs to be filled up with something. So you use an extra plate of steel, an extra piece of steel, and you would call that a filler or a fill plate. And you use those basically just to accommodate gaps that arise when you join different members together. This is another image, 3 images actually, that come off of steelconstruction.info. This is a European website. I think it's from the United Kingdom. And instead of calling them fill plates over there, they call them pack plates or packs. But similar idea, you're just using extra steel that's really not there for a structural purpose. It's basically there just to take up space so that when you bolt it together, you don't end up with bending and warping of the plates. Okay, a second type of I-shaped section that we deal with is an S-shape or a standard shape. American standard beams have flanges that are variable in thickness. The inner surface of the flange has a slope of 2 to 12 or 16.67%. Both the depth and the T dimensions of all S-shapes within a group are the same to permit section changes. And these are used mostly in overhead crane systems. We won't use them very much at all in this class. We might have the odd example problem where we put an S shape in instead of a W shape. Right, so. Okay, H piles or HP shapes are also used from time to time. They're similar to W shapes, except that with an H pile section, the flanges and the web have the same thickness. With a W shape, the flanges are always thicker than the web, but with an H pile shape, the flanges and the web have the same thickness. So like W shapes, the T dimension of all HP shapes is the same to permit section changes with different cross sections, and they're used primarily for substructures or foundation work. So piles, retaining walls, foundations, things of that nature. Miscellaneous I-shaped sections are also used these are basically just I-shaped sections that don't meet the criteria for W, HP, or S sections. Miscellaneous sections are not used that often in structural engineering. They might be used for non-structural applications, like maybe stairwells or things of that nature. Channels are also used fairly often in steel, though not as often as W shapes. They come in 2 different varieties, a C shape and an MC shape. A C shape is known as an American standard channel, and it has flanges that have variable thickness, much like the standard I shape or the S shape. The inner surfaces have a slope of 2 to 12 or 16.67%. MC shapes or miscellaneous channels are shapes that have flanges with a slope other than 16.67% on their inside surface. So just like W shapes or I shape sections, the channels are designated by either a C or an MC, followed by the depth of the section in inches and the weight of the section in units of pounds per foot. So for example, a C12 by 30 is a channel that's 12 inches deep and weighs 30 pounds per foot. The difference is that one difference, rather, is that when you look at the depth of a channel as nominally 12 inches deep, it's actually 12 inches deep. So that's a little bit different than with W shapes. And it doesn't make any sense. There's no really congruity there, but you'll get used to it after you start working with them. So all C and MC shapes within a different group also have the same flange thickness and T dimension as well. The only difference really is the flange width and the thickness of the web. Okay, angle sections are used quite often as well. Angles have legs that have the same thickness on both legs. You can't find a rolled angle in the AISC manual that has 2 different thicknesses for the 2 different legs. They can have the same leg width, or they can have different leg widths depending on the particular angle you're designing with. And the designation here is an L followed by 3 letters. The first is the first, not 3 letters, 3 numbers. The first number is the first leg width, the second number is the second leg width, and the third number is the thickness. So the angle that's shown here on the left would be an L6 by 6 by 3/4. And the angle that's shown here on the right would be an L6 by 4 by 5/8. So the longer leg is the first number that appears in the designation, and the angle that's shown here on the left would be an equal leg angle. Angles are often used in pairs, and when they are, they're designated as 2Ls, 2L something by something by something. They're used in pairs often enough that you actually have properties tabulated in the AISC manual for pairs of angles in addition to just single angles. So you can arrange unequal leg angles 2 different ways. When you arrange them with the longer legs back to back, they're designated as L01b, long legs back to back. When you arrange them the other way, they're designated as SLBB, short legs back to back. And then often on drawings, you'll see them designated as long legs vertical, or short legs horizontal, or something like that, or long legs in the plane of the frame. You'll see that note fairly commonly on structural steel drawings. T-shaped sections are also used with some regularity in steel buildings, and T's are formed by splitting or cutting in half a parent I shape. So you can take a W shape, an M shape, or an S shape and split it in half along its length at the mid depth of the web, and you end up with a T shape. So for example, if you take a W36 by 210 and you cut it in half at the mid depth of the web along its length, then you end up with a WT 18 by 105. So 36 divided by 2 is 18, 210 divided by 2 is 105. Hollow structural sections are another common shape that's you'll find in steel buildings. They come in square sections, rectangular sections, and round sections. So they're designated for rectangulars and rounds as HSS B by H by T. And for round sections, they're designated as HSS D by T. So B is the breadth of the section, or the width, H is the height, and T is the thickness. And then D, of course, would be the diameter for a round section. So one interesting characteristic is that when manufacturers roll these or make these HSS members, often called tube steel, by the way, or for tubes, they make them out of flat stock, and there's a tolerance on the thickness. If you have, say, a 1-inch thick tube, it doesn't necessarily have to be 1 inch. It could be, I'm making up numbers here, it could be as thin as 0.93 inches, or it could be a little bit over thickness, say 1.05 inches in thickness. There's a tolerance range on that. So the manufacturers have gotten good enough that they can actually target the low end of the tolerance. So if they're going to make a tube that's, say, nominally a 10 by 12 by 1 inch tube, they don't actually buy steel that's 1 inch thick. They buy steel that's 0.93 inches thick. So they can save money on the steel and still satisfy the letter of the law, so to speak, with the specifications for the tubes. So as designers, we have to keep that in mind. When we design a tube that's has a nominal thickness, say, of 1 inch, we actually use a smaller thickness, 93% of that, or 0.93 inches for that thickness. And we'll reinforce this with some examples that will work as we go through the semester. So the way tubes are made are to take a piece of flat stock, and then through a series of rolling mills, rolling stands, you actually bend that from a piece of flat, shown as illustration number 1, into a U-shaped section, shown as number 2. Finally, enclose that up, and then they have a resistance weld on one face of the section where the tube is actually welded together. There's a video from, I think it's Atlas Tube, that shows the manufacturing process. That's a pretty cool video. I would encourage you to take a look at that. And if you're ever in one of the big box stores like Walmart or Home Depot or something like that, you can go up to these columns that are exposed, and you can actually look at all four faces, and you can find the weld on one of the four faces of that shape. There are a couple of different grades of material for tube steel or hollow structural sections. You have A500 grade B, or you have ASTM A1085. And this is a bit of a change. So if you're looking at older textbooks or older editions of the manual, they might not have the 1085 steel in there. So basically, the grade here on the left, A500, had two different yield stresses for the steel. It had a 42 KSI yield for rounds. It had a 46 KSI yield for square and rectangular sections. That was kind of a pain to keep track of that, and it also created not a problem, but just an incongruity when you would look at W shapes that are made out of grade 50 steel versus tubes that were made out of 42 or 46 KSI steel. So the new recommended is to go with A1085, where the yield stress for the steel for the tube is 50 KSI, just like that of the W shapes. Also has better characteristics with respect to welding and toughness and things of that nature. But you'll still see a lot of A500 out there, and if you're using an older textbook or older manual, you'll see A500 called out, and you'll see no mention of A1085 at all. Okay, pipe sections are occasionally used in structures. Pipe sections are available in three different grades, either standard, extra strong, or 2 extra strong, double extra strong. And those are basically the weight classes for the pipes. The designation for a pipe section is the nominal diameter, and then the weight class. So they're available up through 12-inch diameter. NPS stands for nominal pipe sizes, and pipes, just like HSSs, are rolled with wall thicknesses that are actually 93% of the nominal. So pipes and tubes, you can find some of them that have the same dimensions. So you might find an HSS 12 by something that has the same diameter as a pipe that has the same thickness. But typically the HSS member is going to be a better steel. They're rolled to different tolerances and things of that nature. So pipes are fine in a lot of cases, used as a post, maybe in a small building, but an HSS is fundamentally just a better steel and a better member. We use flat rolled products quite a bit in structural steel buildings. And this is a table that gives us the proper terminology to use for those products. So if you have a flat piece of steel, it could be a strip, could be a sheet, could be plate, or could be a bar. Just all different names for the same thing, depending on how thick the product is or how wide the product is. Structural steel is considered to be anything that's a 1/4 inch or thicker. So the thinner steel products are referred to as strip or sheet with a thickness less than 0.23 inches here, or 1/4 of an inch roughly. And those are the types of steel products you're going to make a car out of, or washing machines, things of that nature. Products that are a 1/4 inch or thicker are available either as bars or plates. So if you have a width that's less than 8 inches, you call it a bar. If you have a width that's greater than 8 inches, you call it a plate. When you specify plates and bars, you should use these increments for the plate thickness. If the thickness of the plate or bar is less than or equal to 3/8, you specify it in 16-inch increments. Between 3/8 and 1 inch in thickness, you specify in 1/8 inch increments. If you have a thickness greater than 1 inch, then you go to 1/4 inch increments. So you wouldn't want to order a plate that is 2 3/16 inch thick, for example. You wouldn't be able to get that, and you would expose yourself as somebody who doesn't know much about steel. So instead of ordering 2 3/16, you would bump that up, and you would order 2 1/4 inch thick. Bar thicknesses, are specified in 1/8 inch increments, and bar width are specified in 1/4 inch increments. Okay, dimensional tolerances also exist for rolled sections, and they govern everything from the depth of the section to the flange width, and then whether or not the web is at the center of the section. And I've seen that firsthand with some laboratory experiments that we were running. We ordered some specimens in, and I uh, rather foolishly assumed that the web of the cross section would be right at the center of the flanges, and it wasn't, and that created some problems with detailing. So the depth of the section could be plus or minus an eighth of an inch. The flange width could be as much as a quarter inch over or 3/16 under, and the web is allowed to be off center. So these create problems with detailing, and you have to allow for the members to be within these tolerances. I've been on job sites where I've seen iron workers with great big sledgehammers trying to fit a cross section in between two plates because the detailer or the engineer didn't allow for the possibility that the section could be an eighth of an inch deeper than it was really called out in the manual. Okay, there's some other characteristics. These are all covered in ASTM A6, by the way, but the most important parts of that are included in Chapter 1 of the AISC Steel Manual. So you also have tolerances on how parallel the flanges have to be to each other. And so that's interesting as well when you go in and try and fit two pieces of steel together. Okay, camber and sweep are important. Sometimes we provide these on purpose. Sometimes they're provided to us free of charge. So basically, camber and sweep are just variations of the member's axis with respect to a theoretical line. So if the member is bent about its strong axis, about the x-axis, then it's referred to as a camber. If the member is bent about its weak axis or the y-axis, then it's referred to as a sweep. Okay, then here's a tolerance for angles. Angles are supposed to be 90 degrees when you look at an L, but they're not always perfect. So it gives you a tolerance for how out of 90 degrees an angle can be. Another category of steel products for structural applications is cold formed steel. Structural shapes of this type are created by bending thin material such as sheet or strips or sometimes plates into the desired shape without reheating them first. Okay, because of the thinness of the cross-sectional elements, the design of these members are typically governed by instability or buckling, and that's something that's unique about cold form steel. When we look at hot rolled steel sections, then we worry to a much greater extent about things like yielding or developing the yield moment or plastic moment of a cross section in bending. But when we look at cold form steel members, the design problem is all about buckling. Okay, one of the advantages of cold form steel is that you can get just about any conceivable shape manufactured because it's easy to work with. You can also get a higher yield point in the steel from the cold working, but this higher yield strength comes at the expense of a reduction in ductility. So we're not going to talk too much about cold form steel in this class. Most of what we do is going to be a hot rolled steel. The image here, borrowed from a website, it's shown at the bottom of the slide, shows a combination of hot rolled and cold form steel. So if you look at this, the beam here and the column here are going to be hot rolled sections. The reason they show up as silver is because they've been sent through a galvanizing process. And then these sections here are cold form steel members that are used as secondary. And one way, I don't know if this is this could be an HSS here, or it could be a cold form section. I can't see the backside to know for sure. It's screwed in, so it's probably a cold form section. And then here is a tray for cold form and then a stud. Basically, cold form steel to a large extent is used to replace members that would conventionally have been made out of wood. It's lighter than an equivalent wooden shape and is also more durable as well. It's not it doesn't rot. It's not susceptible to termites and things like that. This is an expansion on the Jungle Gyms facility in Fairfield, and they're putting a new bay in, and this shows a good combination of both cold form and hot rolled product. You can see the main members here are hot rolled. They're actually plates that are welded together to form eye shapes, so they're tapered so they can't be rolled. But then up here in the roof system, you can see some cold form sections. So if we zoom in on the roof, you can see that there are cold formed Z-shaped sections. That's a Z-shaped section there, there, and there that form the the framing for the roof. Now there's also some hot rolled sections here. Here's a W shape, or maybe it's a miscellaneous, probably W shape. And that frames in this part of the roof here. And my guess is that that's going to support something heavier, like maybe a rooftop heating unit or air conditioning unit or something like that. So they needed something that was stronger, so they used hot rolled sections in that area instead of cold form sections. This slide shows some common shapes that are used in cold form steel. So up here you have channel sections. Let's see. So they come in 3 different varieties. You have a channel on the left, you have a lipped channel in the center, and then you have a sigma shape or lipped sigma on the right there. So these are lips. And those lips actually act as stiffeners to increase the buckling resistance of that member. Up here you have Z-shaped sections. So you have a Z on the left, a lipped Z in the center, and then a lipped sloped Z on the right. Down here, excuse me, down here in the lower left, you have a couple of different angles. You have an L section and a lipped L. And then here you have a hat section, and then you have a lipped hat over here. Now, there are other cold form sections available. There's catalogs you can get for them. But for the most part, we're not going to deal with cold form steel. One exception to that is metal decking. We're going to use metal decking quite a bit in our project and in some of our example problems. Metal decking is a cold form product, so that's one exception. Okay, we're going to shift gears a little bit now and talk about the mechanical properties, not necessarily the geometric properties of steel. And we have some definitions to start that conversation off with. Strength is the ability of the material to withstand stresses resulting from applied loads. Stiffness is the ability to sustain the loads without too much elastic deformation. So if a member is stiff, it will bend less. It'll have less deflection under load than if it was flexible. Ductility is the ability of the member or the material to sustain inelastic deformations before it fractures. So ductility is basically after it starts to yield, but before it actually fails. That's the measure of ductility. And it's important to us because it provides warnings to the occupants of the building that something is wrong and that they should leave the building before it actually collapses or fails. Toughness is defined as the area under the stress-strain curve for the material, and it's used as a measure of the energy absorption per unit volume for the material. So when we design steel, structural steel, we design for yielding, we design for fracture, and we design for buckling, loosely speaking. There's other considerations, and toughness is an example, is a parameter that gives us an indication of the fracture resistance of a material. Hardness is the ability of the material to resist abrasion, and that's not necessarily something that we look for in structural steel, because when you increase the hardness, then you generally reduce the ductility. And for us as structural engineers, having a higher ductility is more important than having a high hardness. So a hard steel would be important if you were designing tools, for example, like a wrench or a hammer or something like that. You might need the hardness might be more important to you in that case than ductility would. Notch toughness is another measure of the ability to resist fracture. It's the ability to absorb a sudden stress increase without fracturing. And in theory, you guys in your materials of construction class have all seen a Sharpie V-notch test. and which is the basis we use to measure the toughness, or CVN, Sharpie V notch test. Weldability is another characteristic of the steel, and that's the ability of the steel to be welded without having imperfections in it. And in order to improve the weldability of steel, we adjust the chemistry, we adjust the hardness, toughness, etc. And then finally, corrosion resistance is another consideration. By adjusting the chemistry of the steel, we can make it less susceptible to rusting. Weathering steels like A242 or A588, they actually develop a thin layer of rust that's called a patina that protects the remaining steel from further corrosion. And we can impart these characteristics by adding additional copper or nickel or chromium to the chemistry of the steel, and that gives us weathering steel. Okay, here are some of the examples of tests that we use for characterizing properties of steel. We have mechanical testing and non-destructive testing. So by far, the most common test is a tensile test. We take a coupon and put it in a machine and pull on it. We also do toughness testing, hardness testing, and fatigue testing to characterize the performance of the steel product. When we don't want to damage the product, then we can use non-destructive testing like ultrasonics or radiographics, or maybe some dye penetrant. I didn't bother to write that down. But, basically, those are used most often to examine welds after they're made in the shop. So ultrasonic testing is use sound waves that pass through the steel, and they look for imperfections. Radiographic testing is basically the use of X-rays. So this shows an example of a tensile test, and you guys should all have seen this sort of a thing in your materials of construction class. And basically, we take a steel specimen called a coupon, and we put it in a machine that uses hydraulics, usually hydraulics, to apply a tension to it, and we pull on the material until it fails. And we record the displacement and the strain at the same time, and we can develop a stress strain curve for the material. Okay, called out here is a load cell that measures the load that's applied. We have a displacement transducer that in this case is buried in the machine. And then we have two hydraulic grips here that make it easier to actually grip the specimen and install it in the machine. This shows a close-up of a smaller specimen, and this product here in the middle, or this instrument in the middle, is it's called a strain transducer. Now remember the definition of strain. Epsilon is basically the change in length divided by the original length. So using this instrument here, you know what the original length is, and it measures the change in length, and by dividing one by the other, you can get the strain. So the specimens that are tested, the rate of loading and things of that nature are covered in ASTM E8, which covers all metals, and they're also covered in ASTM A370, which covers steel specifically. The coupons that we use could either be flats, like the ones that are shown at the top, or they could be rounds as well. So if you're using round bar, for example, it would be easier to cut a round specimen. If you're looking at a W shape, for example, it's easier to cut a flat specimen. Coupons from rolled sections are cut from the webs of the sections in the direction parallel to the direction of rolling, so parallel to the major length dimension of the product. If you look at the strength of steel in the other dimensions, it can be different. So it's important to specify which direction we cut the coupons in. So usually the direction of rolling is the strongest direction, but fortunately for us, it's usually the direction that the load is applied in as well. Either, well, not necessarily the load, but the stresses resulting from the load. So that works out well. This is a typical stress strain curve. I can't remember which textbook I got this out of. I don't know if it was out of an earlier version of Segui. I scanned it in. You can kind of see the gray around the edge. Or it might be out of Salmon and Johnson, but it shows the general characteristic of a stress strain curve. So of importance here is the yield stress. This is the yield point here. This is the onset of strain hardening. This is the ultimate strength or the tensile strength of the material. So this is the elastic region, linear elastic region of the material. This is the yield plateau here. This is the strain hardening region here. And then this is a region where you actually see the specimen start to neck down before it fractures. Okay, here is a zoomed in version of a slide similar to the one we showed on the last page. And if you have a specimen that's installed very carefully and you test it just right, you can actually see different parts of the yield point. So altogether, I would refer to this as the yield point, but we can be more specific than that. We can say that this is the proportional limit. That's the point at which the material no longer responds in a straight line. This is the elastic limit. This is the upper yield point. This is the lower yield point. You don't see that in all cases. Typically, when you're testing steel, you try and test it at a high rate of speed. You could do more tests in the same amount of time. Plus, the material shows a higher yield point if you test it faster. And you don't always see all of these details, but it's important to understand the difference between the upper yield point and the lower yield point. So basically, as the material comes up along its elastic range, it actually reaches the upper yield point, and then it dips down to a lower yield point, and then it moves on to the yield plateau. So one common way of determining what the actual yield stress is here, instead of taking the upper yield point or the lower yield point, you actually take a line and you create a line that's parallel to the elastic region. So if this is the elastic response of the steel shown here, then what we do is we shift that line over. So if we had a rolling ruler, then we shift that over by some amount. That dimension is usually a dimension that's 0.002 strain, and strain is dimensionless. So that is actually equal to 0.2%. So we have a line that is offset by 0.2%. So we refer to this point up here at the top. Let me get the red pen color. So this right here would be, let's see, and then we strike that over here to the axis on the left. And this would be F sub Y. That would be the 0.2% yield stress for that material. And I think you're asked to do this in one of your homework assignments. All right, now from a design point of view, when we look at steel, there's a lot of different characteristics that we need to know. The yield stress is usually the most important, but also the tensile strength is important as well, or the ultimate strength, F sub U. Modulus of elasticity is taken as constant for all grades of steel. So E is taken as 29,000 KSI, regardless of the grade of steel that you have. The shear modulus of elasticity, G, is taken as 11,200 KSI, regardless of the type of steel you have. And then the strain hardening modulus is not something we usually use explicitly, nor is the percent elongation. But it's important to know that our steel has ductility, and the percent elongation at fracture is a measure of that ductility. So this is a slide that shows actual stress strain data for a grade 50 steel. This is ASTM A572 grade 50. We tested this here at UC probably back in 2008 timeframe. And it gives you an indication of exactly the proportions between the elastic portion of the response, the yield plateau, the strain hardening region, and then the necking and fracture region. So you can see this would be an upper yield point here. There's a lower yield point buried in there. This is basically the yield plateau here. This is the strain hardening region. This is the necking region there. This material over here, or this data rather, is shown in a different color because we took the strain transducer off of the specimen at this point, because we didn't want the fracture of the specimen to damage the strain transducer or the extensometer. So we had to fit that in there using data from the displacement transducer in the machine, as opposed to using the extensometer. A lot of times when we're working with the steel, we don't use the actual stress strain response for the steel, though. It's a little bit more complicated than we need for most of our designs. So we often idealize the response of the steel using an elastic perfectly plastic curve. So basically, we just account for the elastic region and then the yield plateau, and we say that the steel response is bilinear, and we discount the strain hardening region, the necking region, etc. In some cases, when we need to be a little bit more specific, then we'll use a trilinear representation, 3 lines, trilinear. So we have an elastic region, we have a yield plateau, and then we have the strain hardening region. And a lot of times the strain hardening modulus E sub S is approximated as 2% of the elastic modulus E. This shows the stress strain response of a number of different grades of steel. So the lowest curve is a grade 36 steel, A36. That would be a carbon steel, a mild steel, different words for the same thing. The middle curve is grade 50 steel, high strength, low alloy, HSLA steel. And that's the one that you would commonly see for W shapes. Grade 36 steel would be used for angles and for channels by default, but you can get angles and channels in grade 50 steel as well. And then the upper curve is for 100 KSI steel, and we wouldn't use that very much in structural engineering. It would be relatively rare to use a steel that's 100 KSI. There are other intermediate grades of steel. You can get grade 60 or grade 70 steel that's used more and more commonly now. Grade 70 steel is common in bridges, and you can see some columns that that are made out of W shapes rolled from either grade, I think it's 65 or grade 70 steel. So one thing to note is all of these steels, regardless of the grade, have the same elastic modulus, right? So the slope portion of the curve over here on the left is the same. So let me see if I can sketch that in. No, that's not what I want. There we go. And the 0.2% offset method becomes more important with stronger steels because you need a method to identify the yield point when there isn't an apparent yield point. So note here for the 36 grade steel and the 50 grade steel, there's an apparent yield point there, but up here for the 100 KSI steel or the stronger steel, there's no apparent upper yield point. So you need a repeatable way of identifying the yield point there, the yield stress, and that's where the 0.2% offset becomes more important. Also note that the ductility you get is rather good for the grade 36 and grade 50 steel, but when you get to higher strength steels, that ductility is limited compared to the carbon steel or the HSLA steel. Now, that particular trend is illustrated in this slide as well. We have A36 steel again here. We have A572 grade 50 steel. Here's the weathering steel, A588. A913 is a grade of steel that's used for plates. A709 is a bridge steel, etc. A514 would be like 100 KSI steel. But one thing to note is that as you increase the strength of the steel, you have a decreasing ductility in the steel as well. So there's a relationship there that's not quantitative, but it's certainly qualitative, that as you increase the strength of the steel, you have a reduction in the ductility. That ductility is not something that we design for explicitly, but a level of ductility is assumed in the development of the design specifications that we use for steel. Aside from tensile testing, another common test that's used to characterize material properties is a toughness test. Specifically, a Sharpie V-notch test is used to determine the notch toughness of the material. That's the ability of the material to resist a sudden fracture. Sharpie is the person who developed the test, and the V and the notch come from the idea that there's a specimen with a small notch pre-made in it that's shaped like a V. That specimen is placed inside of a test machine in an anvil, and then you have a hammer that's raised to a starting position with a known potential energy. That hammer is then released and swings through the specimen, imparting some of the energy into the specimen when it fractures, and then reaches a lower potential energy on the upswing on the other side. The difference in potential energy from the starting position to the end position is basically the amount of energy that is required to fracture that specimen, and that is reported as the toughness of the material. The toughness of the material is different for different temperatures. If you have a specimen that's tested at 70 degrees Fahrenheit, it will have a higher notch toughness than a specimen that's tested at, say, 0 degrees Fahrenheit. So typically the toughness isn't reported as a single value. It's usually reported as an energy level at a certain temperature, or as the last item here says, it's presented on a toughness transition temperature curve. This is an example of a toughness transition temperature curve and is the result of a number of different toughness tests that are conducted at different temperatures. So typically you would go into a laboratory, you would conduct tests at different temperatures, and you would see a bunch of different data points like this. It's a bit extreme perhaps. You probably wouldn't conduct tests at so many different temperatures, but then you would fit a line to it like this black line that's shown here. And you could see that there is a transition in toughness from a warmer temperature to a toughness at a lower temperature. So say out here at a temperature of about 60 degrees Fahrenheit, you might have a toughness of 50 foot-pounds, whereas down here at a temperature of 0 degrees Fahrenheit, you're looking at a toughness of about 10 foot-pounds. So that's important to us. We need to know what that range of toughness is. If it's a bridge type structure that's erected in Alaska, then it's important to know that our material might not have the same toughness in the winter as it does in the summer, and it might mean that that material should be excluded for use in bridges in Alaska. But that same material might be just fine in Puerto Rico or in Florida. So anyways, toughness is also an important measure. We use Sharpie V-notch toughness testing, and the toughness of the material is a function of the temperature. Hardness testing is also common, but it isn't as important. It's not as tensile strength or as toughness. It's not a primary consideration for us. Hardness can be correlated to strength though. So in some cases where we have material that can't be tested in a tensile strength, in a tensile test, we can test the hardness of the material and then get an idea of what the strength is based on that hardness. So we have a number of different scales that we use: a Rockwell scale, Burnell scale, and a Vickers scale. The Rockwell scale is the most common, and the Rockwell test consists of using a steel or a carbide sphere that's pressed into the steel with a specified force, and the hardness is reported as the depth of the indentation that's left. Okay, there's also the Burnell, which is similar to the Rockwell, except that a carbide sphere is pressed into the steel with a specified force, and then the hardness is reported as the force divided by the surface area of the indentation. So similar, but a little bit more complex to figure out what that surface area is. And then if you're dealing with a very hard material, then you might use a Vickers test where you have a diamond-shaped pyramid that's a diamond pyramid rather, that's pressed into the steel with a specified force for a predetermined length of time, and the hardness is reported as the force divided by the projected area of the resulting indentation. So typically we use Rockwell for most of our steel, so you might see Rockwell B scale or Rockwell C scale depending on the particular steel that you're looking at. So the different scales are needed because, you know, plastic and brass and steel and aluminum, they all have very greatly varying levels of hardness. The apparatus shown on this slide, the apparatuses shown on this slide are a couple of different hardness testers. The one on the left is a digital tester, and the one on the right is analog. Basically, they both have a means of measuring force and either the amount of displacement or indentation or another mechanism to figure out what the surface area is. So we have one of these in the high bay lab, but we don't use it very often, and probably not a part of anything that you did in your materials of construction class. So the last type of testing that we'll talk about is fatigue testing, and I would say that this type of testing is rather rare or uncommon for a typical engineering design project. We could do this type of testing for development of specification language or maybe the qualification of new types of materials. But for you to do this as part of a routine design would be rather uncommon. Basically, though, we have a specimen that's called a trouser leg specimen because if you were to rotate it 90 degrees clockwise, it would look like a pair of trousers, right? But basically, there's a notch that's cut into the material at the beginning using some kind of like a wire EDM or maybe a laser cutter or something like that. And then the test machine just imposes a cyclic tension that ultimately leads to a fatigue crack. And the fatigue crack is outlined here. It basically starts there at the point of concentrated stress. And that crack actually develops and grows from right to left in the screen. And the rate of crack growth can be correlated to the toughness of the material. And then this could be used to evaluate whether the material is acceptable under fatigue consideration or can be used to develop specification language or things of that nature. Okay, so now that we know what the material properties are, the next topic for discussion is where do we find the values that we need for design? If it's a steel project, the best place to look is in the AISC Manual of Steel Construction. Chapter 2 gives us a lot of those parameters, and there's a series of tables at the end of that chapter that tell us what it is that we need to know. So here's a couple of screenshots from those tables, and these give us an idea of the material properties that we're using based on the type of cross section that we're looking at. So for example, if you're looking at a W shape, then what you would do is you would come in and look at this column right here, and you would be looking for cells that are either gray or black. So this cell down here represents a preferred material specification. So if you're using a W section, then you're probably going to want to use A992 material with F sub Y equal to 50 KSI and F sub U equal to 65 KSI. But you could also get the W shape in A572 grade 50 material with the same yield stress and the same tensile strength. Or you could get a W shape in A36 material with F sub Y equal to 36 KSI and F sub U equal to 58 KSI. Bear in mind, though, if you specify a W shape out of A36, it might very well have a material strength that is 50 KSI for yield and 65 KSI for tensile strength. That would be a so-called dual grade steel in that it satisfies the requirements of both A36 and A992, but the material strength is really much higher than what is required for A36. As another example, suppose you wanted a channel section, then you would look in this column here, and the preferred material strength would be A36. So F sub Y equals 36 KSI and F sub U equals 58. Note that the channel section is also available as A572 grade 50. So if you wanted 50 KSI material for that channel, you could get it. Okay, angles are preferred to be an A36 material, but again, they're available in 50 grade material as well. In fact, I've been told by a number of fabricators that most of the angles that are coming onto projects nowadays, even though they satisfy the requirements of A36 steel, really have a tensile strength, yield strength rather, of around 50 KSI. Note that H-piles are a little bit different. They have a preferred material grade of A572 grade 50 as opposed to A992 for the wide flange sections. And then for HSS sections, hollow structural sections, we have two columns, one for rectangulars and one for rounds. And as it stands right now, you can see that the preferred material spec for those is A500 grade B. I'm sorry, A500 grade C rather, but note that A1085 is available, and I expect that when we get to the next edition of the specification, next edition of the manual in 2022, that you'll see those cells down there for A1085 material be the black or the preferred material specification. Okay, the next couple of pages in the manual give us a similar chart for plates and bars. So if you're looking for plate material, the thickness is going to be the independent parameter, the driving consideration. So if you're looking for material that is up to 8 inches thick, then you can get that material either as A36, so like this, with a yield strength of 36 KSI and a tensile strength of 58. Or you could get it up to 4 inches thick. You can get it as grade 50 material, A572 grade 50. And then there's also the caveat: if you get steel that's a steel plate that's greater than 8 inches in thickness, then the material strength drops down from 36 to 32 KSI, and it's just not available in any higher strengths. And then finally, getting ahead of ourselves a little bit, there is a table in here that gives us material properties for common grades of fasteners. So the different grades of fasteners that we typically use are shown here. F3125 is the ASTM specification, and they come in grades A325 and A490, or the twist-off configuration 1852s and 2280s. So then down here we have grades for basically anchor rods and things of that nature. So the last couple of tables in Chapter 2 deal with surface preparation standards, and that's a bit of a right turn for this particular lecture, but it's worth mentioning, and this is as good a place as any, I suppose. SSPC stands for what? The Society of Protective Coatings, something Society for Protective Coatings. And they have SP1, SP2, SP3, etc., which stand for Surface Preparation Level 1, Surface Preparation Level 2, Surface Preparation Level 3. So when you're specifying steel for a project, you might want it just to be solvent cleaned, for example. Maybe you want it to be cleaned with a power tool. Maybe you want it to be pickled. Maybe you want it to be cleaned and painted with a primer. So these different surface preparations give us a means of specifying different surface preps on construction documents that are easily understood by everybody involved. All right, now I wanted to mention that there are a lot of different cross sections that are available in the AISC manual. Not all of them are available for use, however. I don't know how many are actually in the manual. There might be 1,000, but my guess is that if there are 1,000 sections available, there's probably only 300 or 400 of them that you could actually order and have on a job site at any given time. So just because they're in the manual doesn't mean that there are actually steel mills producing them. So it would be unfortunate if you put together a design for your project only to find out that the cross sections or the shapes that you specified weren't available for a fabricator or erector to actually build the structure out of. So AISC maintains a database of availability for shapes, and you can navigate to it using the URL that's shown here. And when you get to that section or that web page, what you'll do is enter the cross section you're interested in, say a W21 by 44 in this instance. And if we enter the data for a W21 by 44 and hit the submit button, then you get these results. And you can see that a W21 by 44 is available in grade A992 and in grade A709. It's rolled by 4 different steel mills. 3 of those are AISC member producers, Ameristeel, Nucor Yamato, and Steel Dynamics. And then you have ArcelorMittal, which is not an AISC member. So the fact that this particular cross-section, the 21 by 44, is rolled by 4 different steel mills is a good indication that you're going to be able to get that on your job when you need it. If it wasn't rolled by any steel mills, or if it was only rolled by 1, for example, then you would want to maybe look into it a bit further before you specified that particular cross-section. How would you do that? Well, if we click on the Nucor Yamato link down at the bottom, then that's this link right here. Then what that does is it takes us to their web page where you can look up a rolling schedule and see when the W21x44 is scheduled to be rolled. This is a rolling schedule for Nucor Yamato, and I don't have too much experience reading these, but if you look here, you can see the 21x44 is scheduled to be rolled during the week of September 6th, I think, and then possibly again during the week of October 25th. I'm not sure what all of the little designations mean, but this is what a rolling schedule looks like. So if you end up working for a fabricator, then you'll probably deal with these a little bit more than you would if you were actually working as a structural engineer. Okay, that brings us to the end of this lecture. Hopefully by now you have an idea of the different cross sections and shapes that are available for use in structural steel buildings and bridges. And you have an idea of the different types of material testing that the steel is subjected to and the material properties that you're going to use as structural engineers. All right, thanks.